Okay, so welcome to this first colloquium of a new series. We stopped with the last colloquium, I think, was cancelled on February 2020. Then we proceeded online because of COVID, as you can imagine. Now they tell us that COVID is around, but we have to live with it. So we start again. Thank you for coming here. I will just tell you that the next colloquium will be devoted to something that we never heard of here, which is climate change. We will give you an announcement in due time. For the time being, I thank my colleague Fosca Giannotti for organizing this first colloquium, and Professor Cesa-Bianchi for being with us. Please, Fosca, come here and introduce the speaker.
Okay, thanks. It's an honor for me to introduce Professor Nicolò Cesa-Bianchi from University of Statale of Milano. So he's one of the most representative scientists of artificial intelligence community in Italy. So we are friends since many years, so it's really a pleasure having him here. So his main interests are on should I speak English? Yeah. On the design of AI algorithms for machine learning, particularly for sequential decision making, graph mining, active learning clustering with queries, and bandit problems. So it's one of the most, the more theoretical scientists in the area that in Italy. He's a co-author of plenty of papers, more than 100 publications, more than 150 publications. But there is a book which is particularly famous in our community, which is Prediction Learning in Games, which has been a sort of masterpiece of the new students in the area of machine learning and gaming. And is a president of the Association for Computational Learning, and it has been active part of the major AI conferences like NeoRIPS, COLT, and DALT. He has plenty of awards, Google Research, Xerox Foundation, and again, Google, IBM, and is one of the active scientists in the ELISE program, which is one of the organization in Europe on artificial intelligence, and is also a member of one of the spoke of the project, the National Project FAIR, Foundation of AI Research, in the spoke which is focused on adaptive AI. Least but not last, recently has become a member of Academy of Lindsay, which is a national organization, but for very prestigious association for scientific institute. It's a very prestigious scientific institutions, and it's particularly relevant for computer scientists because it is the first computer scientist being elected. I don't know what is the process, or nominated or accepted. We don't know the process being part of this prestigious organization. So now the stage is yours. This is about mathematics of machine learning between statistics and game theory.
Okay, thanks a lot for the invitation here. It's very nice. I was remembering that this is my second time. I think the first one was about 14, 15 years ago that I gave a talk here in Scuola Normale. And thanks a lot also for Fosca for your very kind introduction. Actually, I am the second computer scientist in Accademia delle Lincei, Silvio Micali. I'm the first one who lives in Italy. Let's put it this way. Silvio is a foreign member because I think he has a U.S. citizenship. Yeah. So so anyway, I've been working for many years in the theory of machine learning and the design of algorithms with performance guarantees, with mathematical performance guarantees. And yeah, so I think I guess all of you know that machine learning is one of the engines behind the revolution of AI. And it's, you know, it's really the enabling technology of all the famous applications that we have been exposed to in the last few years. So there's machine learning is actually a very broad discipline, and there are at least, typically, there are three main tasks that are recognized in the area. One is the so-called discriminative task, in which a machine is asked to categorize data in a number of different classes. Could be classification, could be regression, and this is typically done through techniques that are called supervised learning. The second one is something that we've been hearing a lot in the last year, is generative AI. That is typically based on unsupervised learning, but not only. And this is, the technology behind OpenAI and other systems we've been playing with and investigating in the last months. And the third one is the so-called reward maximization tasks, typically robot navigation. And the typical technology there is reinforcement learning. Okay, in this talk I will focus, this is about really the mathematical foundations. So not a lot is known about the mathematical foundations of things that are working very well these days, like large language models. There's a lot to understand. And something is known about, a lot is known actually on reinforcement learning, but I would like to give you a little bit of overview on the mathematics behind the data categorization or discriminative tasks. Because it's, I would say, the most elegant and the most, crystallized part of the theory, the crispest part of the theory. Okay, so, yeah, so we move to some to define a mathematical framework through which we want to understand how data categorization, algorithms for data categorization and data classification work. And so the objects we want to learn are classifiers that will map data points in a set of labels. So for simplicity, we consider binary classification, but it's not a big limitation because most of the interesting stuff is already happening when you're doing binary classification, like, classifying whether your email is spam or interesting. This is like canonical task. All right, so we are gonna do supervised learning. So algorithms will be using training examples, which are pairs of data points and labels where the label is what is the desired label for that data point. Okay? The desired label for the data point is, we would say, the ground truth. It really depends on the problem domain. It might be something that we really observe, like when we predict the weather, then we get the ground truth maybe the day after. Or we do investment on the market, or could be some more fuzzy idea like what is this article talking about? Is it talking about economics, finance, politics, and so on and so forth? But we assume that there's every data point will have a possibly desired label. Although this desired label is not necessarily deterministically associated with the data point, it could be stochastically associated. We'll be more precise in the next slide. And so what a learning algorithm gets in order to build a classifier is a training sequence, which is a sequence of these examples. Okay, I have to navigate this thing. All right, so the training sequence will will be the input to a learning algorithm. So you can think of a learning algorithm now like a map from training sequences of examples, which are pairs of data points and the desired label, to a class of a family of classifiers. It could be neural networks, it could be decision trees, it could be whatever you like. But there's some definite set of functions that your learning algorithm will be picking the output from once you feed it with some training sequence of some finite length. Okay? So now, yeah, this sounds reasonable. And, intuitively, what we would like is that, okay, we would like to, design algorithms, A, that will output classifiers. So this is the classifier output by the algorithm A on a training sequence of length m, such that, the classifier is mostly correct on the data points in most cases. In most cases, whenever we have enough data points. Okay, I'm being vague here on purpose because I want to make a theory, and we will have two ways of formalizing this goal. Okay, so we will have a statistical formalization and then a game theoretic formalization. Machine learning is not like a physical object. And so you can actually look at this object through different lenses. So we will look to this object from the lenses of statistics, and then from the lenses through the lenses of game theory. Okay, and this will be kind of interesting in my opinion, because you can draw different intuitions, conclusions, algorithms, of course. Okay. Right, this is exactly what I just said. So I'm consistent with my own slides. And if you have any questions, feel free to interrupt me, okay, at any point. All right, so statistical learning, this is like what most people know about the foundations of machine learning. Oh yes, we assume there is some statistical source behind the data. And this was pioneered by Vladimir Vapnik, this guy here, which characterized learnability in terms of training set size. Okay, so it gives us an informational characterization of what can be learned with finite resources. Okay, and less valiant. This was happening in the mid 70s in Soviet Union. In the mid 80s, less valiant, without knowing what was happening, what happened 10 years ago, 10 years before in the Soviet Union, came up with a theory of learnability for Boolean learning problems. So he's a computer scientist, he's a Turing Award, and which was mainly based on computational complexity and more than information complexity. Okay. So now there is a total reconciliation between these two perspectives. There's actually a very rich thread of research on Boolean learning that deals mostly with computational complexity. And, today we will mostly talk about information complexity. So the amount of data that I need to learn something up to a certain accuracy. Okay, cool. So let's now be a little bit more formal about what we mean by statistical learning. So a statistical learning problem will be, we are talking about binary classification again, so this is given for granted, is defined by some unknown distribution over my examples, which are pairs of data points and labels. So now labels can be stochastic or can be deterministic. Deterministic is a special case of this. And there is some fixed and unknown distribution that is generated by data. So now I'm assuming that examples, all the examples I observe are realizations of IID draws from this distribution. So this gives me all this power of statistics in order to analyze learning algorithms in a proper way. Okay, so the main yardstick through which we measure how good is a classifier is the notion of statistical risk, which in binary classification is just the probability according to the distribution that is generating the data, that the law of the pairs xy, that a given classifier, okay, mess. I don't know what happened. A given classifier, okay, done. that the given classifier H will misclassify the data point of X. Sorry, the label of X. Okay, so that's the main notion of statistical risk. So we can rank classifiers according to their statistical risk, how good they are on a given learning problem for binary classification. All right, so now we'll be especially looking at this quantity, which is what? Okay, if I want to score how good is not a classifier but an algorithm, then I should also take expectation not only over the testing pair, but also over the training set. So now this quantity is the typical risk of a classifier generated on a training set S sub m by a learning algorithm which is given as input a training set of size m. Okay, so the training set, now the expectation is over the random draw of the training set, and now the training set is fed to the algorithm generates a classifier, and then I'm measuring the risk of the classifier. Okay? And so this is the typical risk of this algorithm, of the classifiers generated by this algorithm when I feed the algorithm with the training set of size m. Okay? So I would like typically this quantity to decrease with the training set size. The more data the algorithm sees, the better we'll be able to to predict data from the same distribution. Okay, where are we? Yes, okay, thank you. Okay, so, right, so now we would like to characterize statistical learnability. And learnability is a property of the class of models from which the algorithm draws its models. Okay, so we would say, okay, right, so we assume that the algorithm A picks classifiers from some class H, I don't know, neural networks from a certain, with certain parameters, okay, meta-parameters, hyperparameters, okay. I have the programmable weights of the neural network will give me then all the classifiers in this class, okay. And now I can look at this quantity here. This is the optimal risk given the data distribution in that class of models. This is the best model in the class for that learning problem, okay, for that data distribution. All right. So now, yes. Sure. Yes, exactly. Exactly. This is exactly what is. No, how far you are from? Yeah, so there are various notions of best, because there is the best classifier for the distribution with no constraints is called the Bayes optimal classifier. It could be arbitrarily complicated, but typically we deal with models that are like neural networks of a certain size, so that we restrict our model to a certain class. So our algorithm will only try to learn something from that class because we have limited resources, we cannot learn anything. So now it makes sense to say, okay, I know that the best I can do is this. So this is the best possible risk within the class I'm taking my models from. So now it's meaningful to look at the distance between the typical risk of a classifier output by my algorithm with the best possible risk in the class from which the algorithm is drawing its models.
Maybe to be more precise, would you estimate the distance?
These are real numbers. These are real numbers, right? Because it's risk is a number. It's a probability of mistake.
So it's essentially like Euclidean distance.
No, it's a real line. We're looking at, this is a scalar, and this is a scalar. Okay. Yeah, exactly. Yeah, sure. So this is the probability that the probability of mistake from the distribution of the best model in my class. And this is what algorithm A actually achieves. Okay. Actually, so the distribution D is unknown. Okay, we don't know what is this best optimal model. All we know is that we have an algorithm that will get some finite amount of data and will try to output a model whose risk in expectation with respect to the generation of the training set is as close as possible to the best possible model in the class. This has to be otherwise, okay. Yeah, so if you have any questions on this, please feel free to ask. All right. So now we say that a class of models, say neural networks of a certain size with certain architecture, is learnable if if we can find an algorithm. This is infimum over all algorithm. We can find an algorithm that whose excess risk with respect to the best model in the class vanishes as we increase the training set size. So this is a reasonable requirement. This is saying, look, the more data I give to this algorithm, I would like the algorithm to get arbitrarily close to the best model in the class. Maybe the class is small, and then this is easy. Maybe the class is big, and then this is hard. That's why it's a property of the class. There is another thing I would like to draw your attention upon, is the fact that we are being distribution free. So I would like this guarantee to hold irrespective to the distribution that is generating the data. So a learning algorithm should be good for any data distribution. So this is a quite demanding requirement, okay? Yeah. Can you perhaps say again what a model is? A model in neural network. A model is a classifier. So a map from data points to labels. I'm looking at binary classification. So let's say a neural network, a decision tree, a linear classifier, name it, right? And I get a class of classifiers by looking at the parameters of the model. If I have a linear model, will be the coefficients. If I have neural networks, are the weights. If I have decision trees, there are the different tests I have in the internal nodes. Okay. Yes, that's pretty. Thanks for the question. Okay. So, okay, one of the algorithms that is hardly efficient but kind of natural is the algorithm known as empirical risk minimizer that is minimizing the training error over the class. So this is what typically algorithms tend to do in different flavors. They get a training set and they will try to minimize a notion of error, in this case classification error, over the training set. So the output of the algorithm, out of this algorithm, is an element of the set of minimizers, of models that minimize the training error. What is the training error is the fraction of mistakes on the training set. Okay, this is a statistics. I can measure it. I can look at the model in script H that achieves that. So the main questions is, when is that the class is learnable? What is the best possible algorithm for a learnable class? And if it is learnable, can it be learned by a natural algorithm, an algorithm that minimizes the empirical risk or training error? So these are natural questions. And these are going to be answered in the next couple of slides. Okay, so one nice thing about the fact that we are not making any assumption on the distribution. So we want our criterion is distribution free. Okay, we want the algorithm to be good with respect to any distribution that generates the data. So this gives us, gave in the 70s, thanks to Vapnik and Chervonenkis, a combinatorial characterization of learnability, which is mathematically nice. And essentially it says, okay, I have a notion of dimension, and the notion of dimension is based on the following tree. And you see this tree is constructed from data points. So I have to find a sequence, in this case a sequence of 3 data points, such that for any path on this tree, on this complete binary tree, I find a function in my class that on these data points will produce this classification. So I have 8 possible paths, and I find 8 functions that achieve all these 8 paths on the 3 data points. Okay? So in this case, I would say that this sequence of 3 data points is shattered by my class of functions. The Vapnik-Chevanekis dimension is the length of the longest sequence of examples that is being shattered by my class of functions. So is the depth of the deepest complete binary tree I can construct of this shape. Okay? So let's check whether this makes sense. Okay, if I have a finite class of models, like decision trees up to a certain depth or a certain number of nodes, then clearly, in order to shatter 3 points, I need 2 to the 3 functions. So the VC dimension is at most the log of the size of the class. Okay, this makes sense. Okay. In the case of linear classifiers, yeah, it also makes sense because it's essentially the number of free parameters plus 1 I have. If I have linear classifiers on RD, then the VC dimension is going to be D plus 1. And this is also nice and easy to prove. And I have classes of models that have infinite VC dimension. Like if you run a nearest neighbor classifier, this will produce some model which is corresponds to a Voronoi tessellation of the learning domain. And this thing has a Vapnik-Chevanekis dimension equals to infinity. Okay, so there are simple model classes, and there are complicated, complex model classes. Okay? So the fundamental theorem of statistical learning, as it has become known in the years, is the following. It's telling you that if the VC dimension of a class of models, of a set of classifiers, neural networks, blah, 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 is finite, then I will find an algorithm that learns at this rate. So remember, this is the excess risk. This is the excess, sorry. Sorry, I went. Yeah, this is the excess risk. So basically, I can find an algorithm that, irrespective to the distribution of the data, is converging to the best model in the class H at a rate which is 1 over square root of a data size, of the training set size, and the scaling factor is given by the VC dimension. And in this case, this is already achieved by the simplest algorithm, which is minimizing empirical risk. Nice. If on the contrary, if the VC dimension is infinite, then I won't be able to converge. So for any algorithm, I can find a distribution such that the algorithm is not able to learn on that distribution. It will not converge to the best model of the class. Okay, so that's a sharp characterization. And this actually happens even when the problem is deterministic, and which means that labels are deterministically associated to data points, and I have a model in my class which is perfect. So even if there is a model in my class that is perfectly fitting the data generated by the source, even in the case if my model class is too large, I won't be able to learn according to this learnability criteria. Okay? Okay, so I have this dichotomy. And this is a precise characterization. And so let's focus a little bit on the realizable case. In the realizable case, I actually will learn faster. Instead of learning at rate 1 over square root of a training set size, I will learn at rate 1 over training set size, still depending on the VC dimension. Okay? So if the problem is easier, because I have a model, a perfect model in my class, and my class is simple enough that the VC dimension is finite, then I win big. I will learn faster than the other case, where there is no perfect model in my class. Okay? And however, there's a bad size. Minimizing empirical risk is not optimal anymore. it's solved by a logarithmic factor in the training set size. And only last year, they found let's say 2 years ago, they found the optimal algorithm for the realizable case that exactly achieves this rate, okay? And this is an algorithm that is still reasonably simple. So it's, oh my God, it's, yeah. It's an algorithm that does a majority vote over log m instances of empirical risk minimization, each trained over a random subsample of the original training set. So you give me the training set, I do a order of m subsamples, random subsample of my training set. I train empirical risk minimization of each subsample, and then I take a majority vote. This is actually optimal, and it was a quite remarkable result that appeared not long ago. Okay, so clearly in this case, the optimal algorithm is not an element of H, because the majority of majority vote classifier is not a member of the model class. Majority vote over H is not necessarily a member of H. Okay. Now, no questions here? Yes. Oh, the lower bound. You want to know the lower bound? Yeah. So it's basically exploiting the fact that you can construct these infinite depth trees in which, you know, you can find a function that is a function for each, for trees of arbitrary depth. It's, the lower bound is actually a very simple construction that uses deterministic assignment of points. And it heavily relies on the definition of VC dimension. Essentially, it will tell you that, okay, so you want to get some accuracy, but I can, accuracy epsilon, but I can force you to use, so essentially it goes like this. If you have, so it's actually an interesting question because it's a weak point of this definition. What is the weak point of this definition? Because this is, you know, one disturbing aspect of this definition is the fact that I take the supremum here for any given sample size. So it tells you that for any sample size m, I can find a distribution such that you cannot be accurate on that sample size. But this sounds a bit unreasonable because typically you fix the distribution and then you let the sample size grow. So it's a bit of a shortcoming of this definition. But 3 years ago, some smart people decided that they wanted to fix this problem. So yeah, so this is another notion of learnability that has exactly addresses the problem that it's kind of unreasonable to pretend that I am good on any distribution when the distribution can depend on the size of the training set. This is not real. This is not practical. In practice, the distribution doesn't know anything about my training set size, right? So there is a parallel sort of a variant of this statistical theory that will exactly address this problem. So for now, it's just for the realizable case, assuming that the best model has no classification mistakes in my class. And we are, okay, this is not, oh yes, this is the excess risk because now this is 0. So the excess risk is simply how wrong is this model. And now we want to fix the problem and say, look, I want to say that a class of models is universally learnable at a certain rate if there exists an algorithm that for any distribution, there will be constants that depend on this distribution such that the expected risk of classifiers generated by the algorithm will decrease at this rate depending on these constants that will depend on the distribution. So now I can let the rate depend on the distribution of the data. So it's different, deeply different from what I had before, which was fully distribution free. And now we can ask ourselves how things change if I use this more relaxed notion of learnability, that is universal instead of being distribution free, universal in this precise sense. Okay? So now I let my learning rate depend on the distribution through these constants. Okay. All right, so first of all, everything becomes learnable. Wow. So we weakened it enough that everything has become learnable, but now that the rate makes a difference, and there is a very nice theorem. For each class of binary classifiers, we have three possible things. Either the class is universal learnable at exponential rate, and this rate is optimal. So this is a fast rate. We can learn, recall that this is the case in which the best model has zero risk. So it's a kind of an easy case, the realizable case. Still, it's interesting. The second case in which H is universal learnable, but at the rate 1 over m. This is like the rate in the distribution-free case. Okay, in the distribution-free case, we had 1 over m in the realizable setting. Or H is universal learnable, but is universal learnable at we will converge, but we will converge arbitrarily slow. Okay, so now if VC dimension is finite, then we know that H is learnable in the previous sense and is also universal learnable. And then now we know that it must be learnable at least at linear rate because we already had that result before. We know that this rate is possible if VC dimension is finite. But now we exactly characterize the fact that some of these classes will be much easier because we can learn at exponential rate. So this gives us a finer structure of the things that are learnable, that have VC dimension smaller than finite VC dimension. However, there are classes that are not learnable according to the distribution-free notion, that are learnable in this distribution-dependent case. This is what this theory is buying us. It's making things that were not previously learnable because we had too much of a hard notion of learnability. They become learnable here. Yes? The learning rate, the constants will depend on the distribution, but not the rate. Yes. So the constants can be arbitrarily big, but the rate will be that. For any fixed distribution, we have a constant and the rate. Okay, so there are classes that are not learnable distribution-free, but they are learnable in with this notion. It can even be learnable with exponential rate. So there are things now that now become very easy to learn that were not previously learnable in the distribution-free sense. So this theory opens up a lot more to being able to formulate rigorous learning guarantees for problems that were out of reach in the previous theory. Okay, so this is concluding the statistical part, and I would like to move on the in the last part. This is really also short to online learning. Online learning starts from the idea that in many cases data are not being generated all at once, but they are continuously generated one by one. There's a stream of data that is being generated because I have financial markets, I have sensor networks, I have web, okay, and using interactions on the web. So the learning model can and will be updated every time a new data point arrives. I can adjust my model. And then now if I have this previous thing, which I have a big training set, it doesn't fit because I can train a model with a training set, but then the training set becomes bigger because I have new data. What do I do then? So I want a different notion of learning that fits this scenario in which I have learning streams, data streams instead of data sets. And here we go. So this comes from the theory of repeated games, James Hannan, David Blackwell, and a lot of people like Tom Cover in information theory and in game theory, Dean Foster and Rakesh Vora. They looked at these repeated games, learning in repeated games. However, also the original analysis of the perceptron algorithm in the 60s is also falls in this setting. And more recently, people like Nick Littlestone, this guy, funny guy with a straw hat, and Manfred Warmuth and Volodya Vovk, they, from the computer science community, pioneered this view of learning as a sequential decision-making problem, essentially. Okay, so now, what is the protocol here? So we have some training sequence which is now not generated by any stochastic source, but a completely deterministic, possibly adversarial source. And the adversary will select the next example, reveal the data point to the learner. The learner will output a prediction, which may depend on the previous data points that are being observed and the current data point. And then the adversary will reveal the label to the learner. Okay, so I see the data point, I make a prediction, I see the true label, I know whether I was right or wrong, and then I adjust my model. Okay. So it's a kind of easy to see that there is an inefficient translation between the two settings, but there are also efficient translations. So I can use an algorithm from one setting to the other setting and so on and so forth. Okay, so now what is the analogon of, in this setting, of the notion of excess risk? There is no more risk here because there's no statistics. So the risk is this notion which you may call sequential risk. So what is this? This is the probability, where the probability is just with respect to the learner's internal randomization, and everything in the environment is deterministic, but the learner can be randomized. So the learner sees has seen a bunch of data, sees the current data point, makes a prediction, and then looks at whether the prediction was correct or not, sums up over a sequence of predictions, takes the average and compares with the best model, with the best classifier in the class. So we are still assuming there is a benchmark class, and we want to know that, can I, on average, my fraction of mistakes over a stream will converge to the fraction of mistakes of the best model in this class, okay? Okay. It's the same thing as before, but now we are relaxing the fact that the data come all at once, they will come sequentially, and they are generated by a deterministic source instead of being generated by a stochastic source. Minimax regret is again, okay, I want to take the worst case over the sequence of data because it's adversarial, it's a game theoretic model, I have an opponent that generated my data, and I want the best algorithm over this worst case data sequence. And it's easy to see that this is harder than statistical learning, okay? Because it's data is adversarial, is not statistics. It's not stochastic. So that's the reason. And you can prove exactly this relationship quite easily. So this notion of excess risk is always an upper bound on the notion of statistical risk for a class of predictor that we use as benchmark. Okay, now, the beauty is that there's a very nice notion that is a notion that comes from the VC dimension. So this is the VC dimension that we saw before. Now you see, the VC dimension is the depth of the deepest tree I can construct of this form, such that I can find classifiers in my class that will realize all possible labelings of these 3 data points. Now I relax the fact that I have to use the same data points at each level. So I can use arbitrary data points at each level, not necessarily the same in the siblings. The siblings don't have to be the same. So clearly, I can construct much deeper trees now, because I'm not forced to use the same data point at each level, okay? Everything else is the same. It's still a combinatorial characterization. So now the same thing will apply. Of course, I need to have at least 2 to the depth of the 3 functions and I call this a Littlestone dimension. Again, it's the depth of the deepest tree I can do in this way. And as I said, the Littlestone dimension will be always an upper bound to the VC dimension because of the reason I just mentioned. And there exist classes such that the VC dimension is 1 and the Littlestone dimension is infinity. So online learning is strictly harder than statistical learning, at least for some classes of models. All right, we come. Now, I have a very nice characterization which looks very much the same. We are almost done. There is one more slide. So I have exactly the same rates for a deterministic adversarial learning problem where the algorithm may be randomized. But now instead of the VC dimension, I have the Littlestone dimension as a scaling factor. So if the VC dimension is finite, I have this rate is infinite, then I cannot learn, even when there is some H which makes no mistakes on the learning sequence. And in the realizable case, I learn at faster rate, exactly mimicking the result we had with the VC dimension. Okay? And when the class of models is finite, there is a very simple randomized algorithm which is called exponential weights. It's been studied a lot in this online learning community that achieves this bound, which is suboptimal, because as we saw, Littlestone dimension is always larger than the size of the class, when the class is, than the log of the size of the class. But this algorithm is pretty simple. Final slides, and then I'm done. So let's see a little bit what we, yes, sorry. Ouch. The sequence? No, wait a minute. So I didn't understand your question. So this is, I can construct a sequence which doesn't have to be an IID sequence, right? So I can construct it deterministically because it's a deterministic model. So I can now fool an algorithm very much in a much easier way because I can look at the algorithm and then construct manually a data sequence on which the algorithm will make a lot of mistakes. Before, I could only construct a distribution and then draw the data IID from the distribution. So it's a much weaker. Yeah, the length of the sequence is M. What is T? There was a T somewhere. Oh, sorry. Okay, then there must be a typo. Okay, okay, in this talk, the length of the sequence is M. Any other thing is a typo, sorry. Okay, yeah. Okay, so this is basically the picture. In the statistical case, okay, we'll use this for the final slide. In the statistical case, and without any assumption on the fact that on the performance of the best model in the class, I have this learning rate, which depends on the VC dimension. And yeah, in the realizable case, when the best model in my class can perfectly fit the data that are stochastically generated, I have a faster rate. This is mimicked exactly in the online learning case. However, the algorithm here, the algorithms that achieve this optimal rate are generally inefficient. And then in the case in which the best model in my class will make mistakes on the sequence, so to be clear, in this case, I mean that the adversary can only construct sequences such that there is at least a model in my class that makes no mistakes. Here, instead, the adversary has no restriction on the way the sequence of data is being constructed. Okay? So this is, and here, this result, so this rate, the fact that we have an optimal rate here is a result from 3 years ago. The proof is still non-constructive, so we don't have any explicit algorithm that achieves this rate as an upper bound. But we have a lower bound construction to show that this rate is actually optimal. I find it very nice and beautiful that it's so perfectly matching with, you change in a very nice way your combinatorial characterization of the class, but when you move from statistics to game theory, at least in the distribution-free case, there is a very natural correspondence. And yeah, then we saw that in practice, people might be more interested in notions of statistical learning that will depend on the distribution in a certain way. And this notion of universal learning is able to capture at the finer level the structure of learnability in terms of the model class I'm using, the model class that my algorithm is using. Thank you very much for your attention.
Questions?
Yeah, I think here. Yes. C'è un ragazzo lì.
About the fact that the rate that we have depends in some way over the distribution we give to the classifier. Are there some ways of having maybe an algorithm that has exactly the same VC dimension, let's say, but depending on the fact that the distribution is simpler or harder, you have a different rate? So, like a way to incorporate the fact that the distribution is simpler in a more profound way. Like, I don't know, it's a multivariate Gaussian instead of a...
So first of all, VC dimension is a property of the class of models I'm learning, not of the algorithm. We always take inf over the algorithms because we want to show. Okay, so it's kind of uncomparable, right? So the VC dimension will characterize the distribution field learning, and it tells you that in universal learning, which is this weaker notion, you will have a rate which is at least 1 over m, okay? Order of 1 over m. Now, the fact that you pay attention to the distribution will highlight the fact that in some cases, the model class is simple enough so that irrespective to the distribution, you will have an exponential rate with constants constants also at the exponent in this case, okay, which will depend on the distribution. But the rate is exponential, so you learn much, much faster. Clearly, this is one way. You can provide different other notions of learnability. You can say learnability with respect to distributions that are, smooth over, you can make it up. This is clearly the drive here is to find characterizations that are mathematically simple, nice, and provide insight on the structure of things that can be learned or not. Okay, because it's not clear that a certain definition of learnability will allow you to to give you a nice classification of things like these theories. These theories tells you, okay, it's very simple. Look at this quantity. It's finite, you can learn at this rate. It's not finite, you cannot learn. Okay. Or look at these other things, then, okay, you can learn at this rate, you can learn at this rate, or you will learn, but at some rate, I don't know what rate. There was another question? Yes.
I have a curiosity about the trichotomy of universal learnability. So the very end of the first part, yeah. Yeah,
right.
This
Yes.
one, yeah. So first I was curious, who is this result due to, and do you have a reference?
Yeah. So this is a beautiful result. Shai Moran, Olivier Bousquet, I don't remember all the authors. But this is done, so Shai Moran is a young researcher at Tel Aviv University. I'm collaborating with, by the way, on interpretability stuff. We can talk about it later. and yeah, he was visiting Google Zurich at some point, and this was one of the outcome of this result. So I will give you it's a stock paper. Okay. So theoretical computer science.
The other thing is a bit surprising a priori because it seems to exclude the possibility of other power law rates. Like 1 over m squared, for instance, is not possible.
I call these gap theorems. Mm-hmm. So there are several gap theorems in learning, not several, but I say more than one, that tell you that essentially, problems are either impossible or they are quantized in terms of learning rates.
Okay. Very interesting. Thank you.
Yeah.
So how common is to find problems with VC equal infinity, and also what relation those have with computability?
Okay. Computability, it's a mess. It's a mess, no? Most things, so neural networks are not efficiently learnable. In the sense you cannot minimize a training error over linear classifiers with 0-1 loss, so let alone neural networks. So nothing is efficient, but we can make it. So we have to look at different notions of efficiency that somehow reconcile with the fact that we actually use these things and they work. Yeah, worst case complexity is obviously of no use here. In terms of VC dimension, okay, so essentially, we do use classes with infinite VC dimension. I would say routinely. We do use, sometimes we do use nearest neighbor. We use decision trees. We used to use kernel classifiers. With Gaussian kernel, the VC dimension becomes infinite if you have a kernel classifier with a Gaussian kernel. So then, of course, the trick is that either you don't have a rate, so you may be able to learn if you are good at trading off overfitting and underfitting, but you won't have a rate guaranteed, which is like the third case, you can learn but without a guaranteed rate. Or if you have assumptions, typically smoothness assumptions on the distribution, you will have a rate that is exponential in the dimension, curse of dimensionality. So these are called, non-parametric consistent learning algorithms. You have the power of learning anything you want, but you will pay with a rate that in the best case is going to be exponential in the dimension of your learning problem, so in the number of features. And this is what, what happens. Neural networks are totally parametric, so you fix your architecture and then you try to learn it, and that's fine. So that fits that scenarios. Of course, there are many other things that do not fit this scenario because we don't know exactly the property of the minima that you reach in a neural network.
So I have a question, more a curiosity. Does this learning theory applies also to generative AI?
No, of course, no. I said the first slide. I'm not doing.
Can you give us the intuition? Why not, and what might be a new learning theory for this case? What we have to study for?
Look, generative AI is a probability distribution over strings of arbitrary length, strings of pixels, of proteins, of words, and so on and so forth. So, first of all, unsupervised learning is notoriously hard because there's it's difficult to come up with the mathematical theory of unsupervised learning than of supervised learning because it's more difficult to define what is a good clustering as opposed to what is a bad clustering, no? And so you can do density estimation, you can do different things, level set density estimation, and things like that. But you already start with the wrong foot. Supervised learning is already hard. And then, yeah, you have a very, depends on what you mean by generative AI now. So there's a recent paper I like a lot that tells you why generative models have to hallucinate. So essentially, if your generative model has certain useful properties, then it's bound to hallucinate in the sense that we observe in LLMs. This is like a theory, a cute piece of theory that captures a little thing with a lot of abstractions. But there is no really general theory. There are theories that tell you, if you want to assign a probability distribution over a certain number of strings based on, this is like a sequential, there's a sequential probability assignment which is very much related to coding theory. But these things were studied, these things were already studied a long time ago. Now there's a huge stack of transformers and, we don't know what in between. And this is a level of complexity that is not amenable to any kind of theoretical treatment unless you do some very radical abstractions that might be able to capture certain aspects. So, yeah.
So we are not ready yet.
Yeah, it's still open for
other questions. So thanks all of you for being here, and thanks again, Nicolò.
There will be some refreshments at the end of the first staircase. The local people will be able to guide the others. So the students may have an opportunity to talk to the speaker a bit more.